Example problem 8 reads, 1 cubic meter of ideal gas at atmospheric pressure is held at a temperature of exactly 20 degrees Celsius. A asks us for how many moles of gas there are at 20 degrees Celsius. So you see moles, you should automatically think PV equals nRT, not the combined gas law. So we're looking for moles here. We're looking for N, ultimately, in letter A. So we'll go ahead and just label this A. So it looks like almost nothing that we have here is in its correct units, unfortunately. There's a lot of converting involved in this problem. So let's just start with the way that PV equals nRT goes. So the pressure, they give it to us 101.3 kilopascals. So we have to combine a little bit of what we learned in the metric system lecture with a little bit of what we learned in this lecture. So first you're going to convert from kilopascals to pascals. And the reason why is because all the way on the very first slide of this lecture, you will see a conversion from pascals to ATM. And so ultimately, we need to be in units of ATM because the ideal gas law constant is 0.0821 liters ATM moles in Kelvin. So we have to use all of those units. So before we can convert to ATMs, we need to be in units of pascals. Then we can convert from units of pascals to units of ATM. So you give the 1 to the thing with the prefix and the metric system from kilo, which is times 10 to the third, to the base unit. And we always treat pascals as a base unit. And then so according to this lecture, the very first slide, in 1 ATM, it's a really big number. So 101.325 pascals. And so kilopascals cancels, pascals cancels, and you're left in ATM. So in your calculators, you should type 101.3 times 1 second e to the third divided by 101.325, and you'll end up with 0.9999. So I'm just going to end up keeping it as 0.9997 since a lot of these numbers carry over. I don't want to say 1 ATM because 1 ATM is the standard for conversions, and while that's really close to 1 ATM, it's not actually 1 ATM. So we'll keep it at 9997 ATM. So that's our P, that's our new P. Volume is a really simple conversion. They give it to you here. So you're in 1 cubic meter, and we need to be in liters. So cubic meters to liters, they tell you that in 1 liter, there is 0.001 cubic meter. And so that cancels, and you're left in units of liters. So in your calculator, 1 divided by 0.001 should be 1,000 liters. And that's done. N is what we're looking for, so we're not going to do anything for that. R we know is always going to be the ideal gas constant. And I'm going to put it down here because we do have a conversion for temperature. So 0.0821 liters ATM moles Kelvin. And so for our temperature, we're given it in units of Celsius. So A wants to know at 20 degrees Celsius. Don't know why I put a random degrees on there before putting the number. So 20 degrees Celsius plus 273.15 equals 293.15 Kelvin. So now we're ready to put all of this into the ideal gas law equation. And we're going to do this at the top here because it looks like we've ran out of room at the bottom. So our new pressure is 0.9997 ATM. Our new volume is 1,000 liters equals X is what we're looking for. So which is N, you can put N or X, it doesn't matter. R is always 0.0821 liters ATM moles Kelvin. And our newly calculated temperature is 293.15 Kelvin. So again, we're going to treat all of this as one variable. We're going to divide by 0.0821 liters ATM moles in Kelvin times 293.15 Kelvin. And so that all cancels. X is left by itself on this side of the equal sign. So we're going to go ahead and divide by 0.0821 liters ATM moles Kelvin. And then 293.15 Kelvin. So I'm actually going to put this all into my calculator as one big calculation for the sake of quickness. So if you want to do this with me, open parentheses, 0.9997, close parentheses, open parentheses, 1000, close parentheses, divided by, open parentheses, 0.0821, close parentheses, open parentheses, 293.15, close parentheses. And so we end up with a N of 41.537, so 41.54 moles. And that is going to be the answer to letter A. And so we'll need to bring that over to the next page for letters B, C, and D because we're not going to have any room to do those over here. So we're starting out with 41.54 moles. Letter B asks us to find the mass of gas in units of kilograms if it's all O2. So we want to know kilograms for O2. So we're going to say moles of O2. We're going to convert moles of O2 to grams of O2. And then we're going to convert grams of O2 to kilograms of O2. So in 1 mole, you need a periodic table to do this. Oxygen is element number 8. The mass of that is 16. And so 16 times 2 equals 32 grams. So that's going to be 32. Remember, oxygen is always diatomic. And so there's always going to be 1 mole is going to be 32 grams for O2, diatomic O2. And then you give the 1 to the thing with the prefix here and the metric system constant to the base unit, which is going to be grams. So moles of O2 cancel, grams of O2 cancel, and you're left in kilograms of O2. So 41.54 times 32 divided by 1 times 10 to the third equals 1.329, so 1.33 kilograms of O2. And that's going to be our answer for B.